welcome back to part 2 of this video where we're looking at sampling distribution models. So the question is, can we always use a normal model? And it just so happens that as long as we have the right conditions, the sampling distribution of sample proportions can be modeled by a normal model pretty well. But you have to check the following assumptions and conditions. The first assumption you're going to check is what's known as the independence assumption, which just says that individuals in a sample must be independent of each other. Now, since sometimes it's really difficult to tell whether this assumption is true, and that's why it is called an assumption, we can check two conditions that will help us verify the independence assumption. The first condition is called the randomization condition, which just says subjects should be randomly assigned to treatments, or if it doesn't say that, you can assume that the sample is representative of the population. And then the other condition you want to check is what's called the 10% condition. A sample size must always be less than 10% of the population. If it's not, then we have other statistical techniques that we use, but that's outside of what we cover in the course. The second assumption is known as the sample size assumption, and the way we check to make sure that the sample size is large enough, we verify what's called the success failure condition, which just says that the sample size has to be large enough for us to expect to see at least 10 successes and 10 failures. So P is the probability of success, and Q, or N minus P, as we talked about in the last video, is the probability of failure. And when you multiply the sample size times P and the sample size times Q, it always has to be greater than or equal to 10. So as long as all of those conditions check, then that means we can use the normal model to approximate the sampling distribution. So no longer is a proportion something we just compute for a set of data. We now see a sample proportion to be a random variable that has a probability distribution. And we have a model for this distribution. We call it the sampling distribution model for a sample proportion. And here's what we know about that. So provided that the sampled values are independent and the sample size is large enough, there's your two assumptions, the sampling distribution of p hat can be reasonably modeled by a normal model where the mean of p hat is just going to be p, and the standard deviation of p hat is equal to the square root of p times q over n. Remember, q is just 1 minus p. Sampling models are what make statistics work. They inform us about the information or amount of variation we should expect when we sample. A sampling distribution model tells us how surprising a sample statistic is and enables us to make informed decisions about how precisely our estimate of the true value of a parameter, remember that is for populations, might be. In other words, sampling distribution models enable us to say something about the population when all we have are data from our sample. And that's why it's important to be able to draw a good sample. And we talked about valid ways to do that back in chapter 11. Okay, please pause the video and read the example, and then we'll solve this together. The Centers for Disease Control and Prevention report that 22% of 18-year-old women in the United States have a body mass index of 25 or more, a value considered by the National Heart, Lung, and Blood Institute to be associated with increased health risks. As part of a routine health check at a large college, the physical education department usually requires students to come in to be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights, from which their BMIs could be calculated. Only 31 of these students had BMIs greater than 25. Is this proportion of high body mass index students unusually small. So the first thing we need to do to see if we can use the normal model to approximate our sampling distribution for p hat, since we're dealing with proportions, is to check our conditions. And remember, the first thing we need to check is the independence assumption. And the way we'll check that is from the randomization condition and the less than 10% condition. So it does say in the problem that 200 randomly selected female students basically self-reported their heights and weights, right? So that covers the randomness. The next condition I need to check to satisfy the independence assumption is the less than 10% condition. So just ask yourself, are the 200 students less than 10% of all female students at a large college? Yes, that would be reasonable to say. So that satisfies the independence assumption. Now, for the sample size assumption, and your book refers to it as the sample size assumption, you need to check the success failure condition. So for the success failure condition, we have to do n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. So n is my sample size, which is 200, and p is the proportion of students that have a body mass index greater than 25. And for that, we need to look back at the problem. My population, right? P is your parameter, and the population is 22% of 18-year-old women have a body mass index of 25 or more. So that's P. And I have to make sure that that is greater than or equal to 10. And then 200 times Q, and Q is just 1 minus P, also has to be greater than or equal to 10. And when I multiply 200 times 0.22, I get 44, which obviously is greater than or equal to 10. And then 200 times 0.78 is 156, which, by the way, you can also get from doing 200 minus 44 is 156. That's also greater than or equal to 10. So all of my conditions checked, which means my independence assumption and my sample size assumption are satisfied. So therefore, you can use a normal model. Okay. So I need to calculate some things here. What I'm going to need is my P, which is my population proportion, which I know is 0.22. And I got that from the problem where it said that 22% of 18-year-old women in the United States have a body mass index of 25 or more. And we also used P when we were calculating the success failure condition. So I have that. I also need to find P hat, and P hat is my sample proportion. So of the 200 randomly sampled or self-selected females, 31 had a BMIs greater than 25. So I just need to divide that, 31 divided by 200. So if we type that in, and I'm just going to use Desmos for this. You can use your graphing calculators. I get 0.155. So that's P hat. That's my sample proportion. And while I'm at it, another calculation I need to do is I need to find the standard deviation of P hat. And if you'll recall, the formula was the square root of P times Q over N. So I know P again is 0.22. Q is just 1 minus 0.22. And then N is 200. So now we're going to type that in. So we have the square root of 0.22 times 0.78. And then we're going to divide that all by 200. And we get 0.029. So that's our standard deviation. So basically what we have going on here right now, if we look at the model, we have a normal model, which I'm attempting to draw here. And in the middle is P. So P, remember, is 0.22. And then we could go 3 standard deviations in either direction. Okay, and what I would do is I would just add 0.22 plus 0.029, and I would keep doing that to get my next increment. So if I do 0.22 plus 0.029, I get 0.249. And then if I add another 0.029, I get 0.278. And then plus 0.029, I get 0.307. And then to go backwards, I'm just going to do 0.22 minus 0.029, and I get 0.191. And then minus 0.029, that gives me 0.162. And then one more time, 0.029, it's 0.133. And remember, my question I'm trying to answer is this proportion, the 31 over 200, of high BMI students unusually small? Okay, so I need to kind of figure out where's the 0.155 going. Well, I know it's going to go somewhere in here, right? How do I find the exact value? I could find the z-score. So how do I find z? Remember, it's the value, which is your sample proportion, minus the mean, which is p, divided by the standard deviation of your p-hat sampling distribution. So here it's just going to be 0.155 minus p, which is 0.22, and then divided by 0.029. And when you do that, you end up with negative 2.24. So that's your z. So that tells me that my sample statistic, my p-hat, is somewhere in here, because that's negative 2.24 standard deviations below. So is our statistic unusually small? Well, if we just estimate here, according to the empirical rule, if you'll remember, 95% of the data values are within 2 standard deviations of the mean. So that tells me that the leftover would be 100 minus 95, which is 5%. And since the normal curve is symmetric, we divide by 2. So that tells me that the values that are more than 2 standard deviations away from the mean show up less than 2.5% of the time. So it is unusually small. Maybe the women at this college differ from the general population, or since they were self-reporting, maybe that might not be accurate. Please feel free to pause the video again and answer these questions. And this will also refer back to the applet that you were asked to look at that will help you understand what's going on here. So you want to poll a random sample of 100 students at a large university to see if they are in favor of the proposed location for the new student center. Of course, you'll get just one number, your sample proportion, p-hat. But if you imagined all the possible samples of 100 students you could draw, and imagine the histogram of all sample proportions from these samples, what shape would it have? And your answer should be a normal model, approximately. Where would the center of that histogram be? So we don't have an actual number, but it should be at P, right? Which is the actual proportion of all students who are in favor. So remember that's P. And if you think that about half the students are in favor of the plan, what would be the standard deviation of the sample proportions? So I need to find the standard deviation of P hat, which remember is the square root of P, which in this case is 0.5, times Q, which is 1 minus 0.5. That just gives me 0.5 again. And then we are sampling 100 students. So we're going to divide by 100. And if you simplify that, you get 0.05. So that would be the standard deviation of the sample proportions. Okay, let's try another problem. You can pause the video to read it and then unpause when you're ready to go over it. Suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats that have the built-in desk on the left rather than the right arm of the chair. In a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? And remember to think, show, tell here. So if you'll recall, the first thing you need to do is check your assumptions. And the first is the independence assumption. So it's pretty reasonable to assume that the enrollment of one left-handed student doesn't affect the other left-hand students from enrolling, right? So my independence assumption is satisfied. Okay, the next one I need to check is the random condition. So it does say here in a class of 90 students. It doesn't say random, but we can assume that the 90 students is a random sample of all students. You can even say the representative of all students. I need to check the 10% condition, which says that the sample must be less than 10% of the population of all students. And we know, of course, that 90 students is less than 10% of all students. And then I also need to check the success failure condition, which satisfies the sample size assumption. So remember, that's n times p. And p here is 0.13 because it says that 13% of the population is left-handed. And that has to be greater than or equal to 10. And n times 1 minus p also has to be greater than or equal to 10. And in both instances, that is the case. So here we get 11.7, and then you can just do 90 minus 11.7. You get 78.3. Both of those are greater than or equal to 10. So that means it's okay to use the normal model. So let's draw the normal model. And let's think about what we need. I know that P is going to go in the center, so that's 0.13. Okay, I need to know how to label all these. And I'm going to go 3 standard deviations in either direction. Okay, so the way I can figure that out is I can find the standard deviation of P hat, which remember is the square root of P, times Q, which is just 1 minus P, and then divided by n, which is 90. And when you simplify that, you get 0.035. So if you recall from the last problem we did, we're going to add 0.035 to 0.13 to go 3 standard deviations out, and then we'll subtract 0.035 to go left. So you should get the following numbers. Okay, so I need to find where p hat's going to go. So to do that, I need to find the z-score. And p hat here is just going to be 15 divided by 200, because it tells me here they're in a 200-seat school auditorium. There's been 15 left-handed seats. So 15 divided by 200 is my p hat. P, we know, is 0.13. And then my standard deviation is 0.035. Okay, and you can always change 15 over 200 to a decimal. So 15 divided by 200 gives me 0.167. So we can put that here in place of that. But I just want to make sure everybody knew where that was coming from. And then when you do the math, you get 1.06. So that means that 0.167 is about a little bit over 1 standard deviation above the mean. And what we're looking for here again is what's the probability there will not be enough seats for the left-handed student. So where would I shade if I'm looking to see if there's enough left-handed seats for students? Well, if there's not enough, it's going to be to the right, because that's telling me that there's more than that percentage of left-handed seats. So I'm finding the probability then that z is going to be greater than, because I'm shading to the right, so that's greater than 1.06, which is, remember, where your flag is. That's your z-score. So to do that, I'm going to, you could use a z-table, but I'm going to use technology. And remember, we're going to use normal CDF for this, and it's found under second vars. So I'm going to go to my graphing calculator, and I'm going to go to second and then vars, and we're picking number 2, normal CDF. For your lower bound, it would be the flag, which is 1.06, and then you're going to put a comma, and then your upper bound is just a really high z-score, so we can use like 100, and then the mean is 0, and the standard deviation is 1. And then hit enter, and then there is your answer. So 0.1446. So what that means is there's about a 14.5 or 14.5% chance that there will not be enough left-handed seats. And that's it for this video. Please stay tuned for the next one, where we'll talk about simulating the sampling distribution of a mean.